preparing recording. Yes. All right, this is just the intro to logarithms, intro to logs. And they have like a mystique to it. You know, it's something that's kind of intimidating. We're going to later learn about a special letter E. We're going to learn about the natural log. Those are related. We have logs. You know, these are the symbols we're going to start to use. And everyone's going to need actually a calculator. So go ahead and get out your phone if you don't have it out. Have the calculator on. If you have your TI-84 or whatnot, go ahead and have it handy. You know, you won't even need that much. You can have just a basic calculator like so. The logarithmic buttons are all pretty standard. Okay, and then I want you to think about this. In some cases, we can figure this out. In some cases, you know, if we knew that the y value was 100, what is my x value? 2. 2. Easy when we know it, right? Yes. Okay. Now, this, we're going to learn how to do the inverse. Take the inverse of an exponent problem here. And just some basic vocabulary. Mostly what we're going to do with today is base 10. Base 10 is the most common, so if we were doing the log, we wouldn't even write the log base 10 of, you know, x. We would just write the log of x. Okay. The base 10, I'm just talking about base 10 at the moment. Don't get too far ahead. The base 10 in our society just means that once you get to 10, the 10th digit, so 10 ones, then you move over a place and it's in the tens digit. Okay. So you say, well, that seems like that's how math works, right? You count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the 10th number, you put a new, you know, we got 1 through 9, and then once you get to 10, you have to put a new space, and then you start counting it again. Every time you get through 10 ones, you would add another to the tens. This is the basic way numbers work, right? Okay. But this is not how all numbers work. There are systems. There's one in, it's somewhere in Micronesia, but they had a method of counting fish. They had it where they were using a base 6 system. In a base 6 system, 1, 2, 3, 4, 5, 6. Well, I guess it would be 6. And then you count again. Every 6th number you would add to the 10th place. This is a whole system, and some like math riddles are, you know, translating what would base 10 be, you know, base 10 to the 6th, what would that be in base 6? So flipping it around, thinking of how to even count numbers, how you use numbers, this is the base 10 system that we're all used to. Okay, so mostly what we're going to be dealing with today is base 10. We won't actually be thinking about it that way, because within the log system, whatever base you're dealing with, we can have this, and we're going to actually do this, I think, as our closure. What is the base here? I mean, that's exponent, that's the base. So this is base 2, okay? And if you think about that, since we're using the exponent for these base values, it's units of 2 being multiplied by itself. Multiplied by itself. Like a base 10 is multiplied by itself. You go from 10 to what? 100 to 1,000 to 10,000. You see how it's like a value based on that base 10. What's that? Yes. All right. So we're going to start by playing around with something here, and we're going to use our calculators. I need somebody to give me a number. Okay, raise your hand. Give me a number 10. Gene Garcia. All right, give me a number between 1 and 100. Raise your hand. I'm calling someone I don't usually call on. Lauren. 71. Okay, so we're going to set this up like so. I want you just using this. No, if you know how to use logs, don't use them yet. It'll be obvious if you're cheating. And I want you to first, let's take a guess here. So, one sec. If I have 10 to the first, what do I have? 10. If I have 10 to the 10 to the second, 100. 10 to the third. Okay, and let's do one more. 10 to the fourth. Third. That's third. That's fourth. 10,000. Okay, good. All right, and 10 to the 0. 1. Okay. So you can see with base 10, we have these values that we get. So if I'm looking for 10 raised to some number to get 71, whereabouts is it going to fit? Between here somewhere, right? 71 fits somewhere in there. So I know that it's not going to be 10 to the first power. That's not enough. 10 to the second is too far. It's going to be some decimal. I want you to force it and work with finding as many decimal places you can to get as close as you can to 71. So no using log buttons, no using what we're learning today. I want you to 10, put raised to the exponent, try 1.5. And in fact, somebody do that. 10 to the 1.5, where does that get us? How much?
Oh, no, my...
No? 10 raised to the 1.5? Say again? 31.62, obviously not enough. Okay, so keep narrowing it down, maybe do a high bid, a low bid. And you're going to write down these numbers. The winner that gets the most digits in accuracy is going to get 2 pieces of candy of your choice. And I'll tell you that the winners of this in period 1 were in the mid-teens. Mid-teens, as in maybe 15 digits, 15 decimal places, 16 decimal places. You're not going to worry about that. Just go ahead and use the process. Get closer and closer. So you don't want to go over. Obviously, if you go over, there's no number the next that you can make go down. So keep them below that 71. Well, we can have exponents that are decimal places. We have exponents that are fractions. So, can't be sure. You won't be able to do much of this. But think of it this way. This is like
we're not going over.
You don't go over. If you go over, that's the wrong decimal place. You're always trying to get under, because if you go over 71, there's no next digit you can put to make it go down. We're always adding. So this would be like 10 to the 3 halves. Maybe just to verify that it works mentally. Think of it as like a decimal, which if you really had to, you could convert any decimal into a fraction. Right. So this implies really that you're 10 to the 1.5 is implying that you take 10 qubits and make it square root. We're going to be getting into the 10 decimal places right now, so don't break your brain trying to figure that out. You could do it. You could do it. All right. Let's see. Getting closer? Keep going. I'm going to give you another minute. Writing them down. You got what? So you can only get closer and closer. It's not like you're going to get to a decimal place and say that actually equals exactly 71. It's going to get closer and closer and closer to it. Because 10 can't be squared, or can't have an exponent of 10 to actually have 71. So it's going to be. So you're going to have a lot of decimal places, though. Okay, just a little competition.
There's more numbers. What?
There's way more numbers.
So I got as far as my calculator to let me go.
Wow.
It's only 10 digits though.
Okay, you got more? Transform it into, or throw it on your phone sideways.
Yeah, still let me
What
know.
about like 7? Can you add another digit? 7? It won't let you.
Yeah, mine will let me.
That's strange. I don't know how the student this morning got 17 digits.
They probably had like a different calculator than mine.
I thought he was using his phone. That's pretty good. Alright, let's see. Yeah. Alright, sounds like some of you maxed out your calculator. So somebody this morning must have had just a heftier calculator here. Let me go ahead and put up what we had this morning. You could see if we'll see how far you got with it. How about that? All right, here we go. We have Oh, this was 61. That won't work. I guess I'm gonna take it. I'm gonna take it from you guys. All right. So we have this is equal to 10 raised to what power? We got say it together. 1.8. 5.
1, 2, 5, 8, 3, 4, 5, 7.
Wait.
8, 7.
3, 4, 8, 7. Don't mess it up on purpose, please. Don't mess it up on purpose. That's an old joke. 3, 4, 8, 7. 1. 9. Anyone haven't passed that?
I just jammed a ton of ones after that because technically didn't read the evening. We got 1.
Is there anything past 9 that someone got? 1? You got it? Anything after 1?
2. No, I'm thinking.
Yeah, I know. Anyone after 1? Is that as far as you got? Did anybody else get to 1 other than Nathan?
I mean, I did put another one after it. Like 1 after 1.
That's like another 1.
Oh my god, 9.
How many?
Another 1.
How many?
Another one.
Is that it?
I don't know. Yeah, I just kept spamming 1.
Yeah.
See, we have a big after over here.
Okay, let's pause the discussion. Pause the discussion. There may be another number missing, but what's the breakthrough? Maybe it has to do with the number missing.
I just put a 2 at the end. Got 70.
Oh, really? So it's rounding because it has a limit on number of digits. So once you max that digit, it does round it. Because you can't go further. There's no conclusive winner for this. I don't know if there's 5 ones repeating like that. Is there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They got a few more digits.
We can do this.
They got 4 more digits.
It's okay. We don't have to do it because that was just an intro. You guys got the game. Very good. All right. 13. There's too many people to give everyone the candy. Question.
Okay, so that's supposed to be like a never-ending number, right? You're never supposed to be able to reach 71.
I don't want to say that for sure, but
Because
yeah.
I just
Why?
put in that to 1,
Right.
and I got exactly 71.
And again, it may be because at the limit of what your calculator can handle with digits, you know, it will just assume that you've got there if you go to that next digit that it can accommodate. You see what I mean? Like, I'd be curious if you put in like a 2 instead of the next number.
I got 71 too.
All right. Next. Does it get you 71 as well? No, don't worry. It's going to be a lot to do. All right, we're going to try one more. We're going to try one more quicker because we got it now. Let's see. Ellie, give me a number between 100 and 1,000. All right, here's your next challenge. 112. We know it's greater than what number and less than what number? Almost. It's between 2 and 3. So let's see how many digits we can get to that. I think we all know the name of the game now.
What's it called?
It's called Find the Number. It's called Log. It's called Let's Get This Log Rolling.
No, please don't take that.
Oh man,
It's gonna make
that's the new name.
No. It's gonna make all the other classes cringe. That's crazy.
Is it rolling or rolling?
It's rolling apostrophe. And see, it's hit. It's like a math game.
I think it's only hit because that.
We should have a day that we only play cool math games. It's in the name.
You guys are. It's rainy day craziness in here. Not craziness. It's just rainy day.
It's also teenage.
Teenage.
I feel like it's better though because it's not changing at all.
You guys, I know too. That's why I'm more patient than most.
So you know what chance?
Working?
Yes.
Or cracking pistachios?
Well, I'm taking a snack break.
Okay.
2, 0.
I'm only going to give you another 90 seconds for this. Get as many as you can. But this will make it so that we're actually not just find the end. People get as far as they can in 90 seconds. It is. All right, another 20 seconds. We stop at 142. Can't read this. All right, and that's time. We're going to count them out together. If you got the furthest, you're going to be the last one talking. All right, so let's go ahead and break it down. This is 10 to the 2. Point. 0.
4, 9, 2, 1, 8, 0, 2, 2, 9.
Wait, 2, 2.
2.
2, 2, 2.
6, 9. I think my calculator maxed out.
I got 2, 3, 4.
You got 2, 3, 4?
Yeah.
Yeah, I think my calculator maxed out.
I got to 2. I feel like
2, 3. So a lot of people stop there. 2, 3.
4.
4.
And then mine maxed out.
Okay, did anyone get the last 3, 4?
I thought mine was different. So mine was 2, 2, 6.
2, 2, 6, or 2, 3, 4? Did yours max out? Yours maxed out.
I got 2, 3.
You got 2, 3, and it maxed out?
I maxed out at
No, but I just gave up after that.
Again, no conclusive winner. We've only seen the limitations of our calculators. Wouldn't it be nice if there was a button that would find these answers right away?
I know, right?
I'm not gonna lie, I won when I stayed out of the game.
You know of this button. All right, we're going to get to that in a moment. Before we do that, all right, so enough. We're going to have enough of the moment of kind of sharing like this with the numbers. We're going to look at just some exponent rules I need to remind you of. And then from there, with learning what the log does, we're going to be able to solve. This isn't the exit. I was just example. So let's look at the properties of exponents for adding. We're going to have subtracting. We're going to have when you have an exponent of 0. And we're going to have just these to start. Gene?
So,
We're done with this. You're talking about something new?
yeah.
Okay.
So when you press a log button on you calculate and put whatever number, right? Like I'm going to put 5, maybe 0.6, right?
Right. I'm not going to actually give you the syntax because everyone is different. I'm not going to mislead others.
But I was wondering, like, that's assuming that I have a base 10. So what if I want to get 5 but in base 12?
There's another syntax on your computer you'll have to do. And actually part of that is I'm going to get to. So hold tight, hold tight. All right, if we have x, let's see, x squared and let's go ahead and do x squared. I'm going to add the, oh, here we go. Right. Don't recall if we did it in the log functions yet. I'm going to go and just put it up here. All right, so you have 10 to the 2nd plus 10 to the 4th. Base 9, 10 to the 4th. No, this isn't where I want to go. One moment. Oh, that's how it is. Okay. Let's say I'm just going to use variables. Okay. If you have two exponents that are added together, right? What can we do with those exponents let's see. So essentially, I think of this as put in some numbers in there to kind of reinforce it. Say if we had this going on, right? What is going to be the outcome of this exponent rule? You guys remember when we add exponents? It's probably going in the other direction. This is really strange because I'm going to put it in the other direction, and we're going to see that we're going to add it. So when we have x squared times x to the third, what do we end up with our exponent? Okay, so this was trying to go backwards. I don't find that helpful. If you ever forget any exponent rules, you can always expand it or use a simple example to remember the rule by expanding it. All this is multiplied together, so what are we going to have? X to the fifth. So essentially we just add it. Okay. Just the basic remembering how we do the exponents. Okay, so subtraction, what if we have this? X to the fifth over x to the third. If you forget, x equals x squared. We are subtracting. See? Just remembering this because logs and logs and exponents are inverse of each other and they have all the same properties. So if you know the properties of exponents, you already know how these things work. We just have to get used to how the syntax of it's most important. And this one's really straightforward. X to the 0. Anything to the 0. Okay. Oh, we did have it. This is another one. It's really multiplication. When we have x to the second times 3, what do we end up with that? X to the sixth. When you have two exponents that are multiplied together, which is going to happen, right? So for instance, if you had, well, we'll stop there. These are the four main properties that we're going to use for exponents and in that sense for logs. Okay. Now, it's really just a spatial kind of, every time. I'm not sure what accent that sounds like to me. But it does sound spatial. All right, a spatial relationship. Okay, so let's go and jot this one down here. Log, or let's start with this. 10 to what exponent gives you x? And in essence, x could be any number, and really what we're trying to find out, just like in our warm-up activity, we're trying to find what exponent will raise us to that 71 or that 112 and whatnot. Okay, so what we do is, what is the base? What is the, really? All right, give me a store.
That's fine.
That's fine. What are those two
Chili's.
called?
Don't talk about
The
Chili's.
Geek Squad.
Chili's.
Best Buy Geek Squad can help you. All right, no problem. She didn't want to joke. Aaron, you gotta go to the office real quick.
Is that Mr. Logan used to it?
I don't even know who that was. Most of the office people love it. It's a question.
Was that Mr. Logan?
No, it wasn't. She always laughs at it.
Oh.
Wait, what did they say?
They said they need Aaron. They didn't laugh or anything. They said, okay, fine, we need Aaron.
I feel like they need some laughter. Yeah.
No.
Like,
That's what I'm trying to do.
like in a continuous day.
Yeah. Welcome, Chili's. Yeah. All right, here we go. As far as the exponents go in general, what is 10 called? We call the 10 what? That's the base. It is related to within the log, it's base 10. The base 10 is a subscript. We write it as log base 10, right? Of x is equal to a. This is what we're trying to figure out. Now, this is AKA. This is also just called log of x is equal to a. Okay. So, in essence, when we had this situation where we had 10 raised to the a is equal to, what was it, 1/12, right? All we have to do, what do we have to do to actually find the a value in its entirety, at least what our calculator can handle? What would we have to do?
Yeah.
Yes. It is log, right? 1/12, and that's going to give us our a. It does have the 10 there, but because 10 is the standard. 10 is the standard of our number system that we use. The log without any base given, when it's just log of 112, that's the same as log base 10 of 112. Okay. So I want you to go ahead on your calculators. Let's go ahead and input the log of 112, and we'll see what values we get for A. And I really wish I would have kept it up here, but I didn't. All right. So you guys figure that out on your calculator. You learn which number you have to push first, before the button or after the button. Okay. If you didn't remember, you could go ahead and do one that you do know. So 10A, and it's 100. So if you do log 100, I want you to do log 100. What do you get? Do log of 100? 2. You see how it works? Anytime you forget, if you have a really complicated number, it's really hard to double check if you understand the syntax. So anytime you forget, I want you to use something you absolutely know, right? Just like the rules for percent fraction, decimal, use 1/2 because we know those versions automatically. So it's the same kind of idea. We're going to go ahead and just list a few of these numbers for 112. Gene, do you have those numbers? Or you have another question?
I do. I have a question.
Ready?
I calculate the numbers anymore.
Who has the numbers already on their calculator ready to go? All right, Lincoln, say them loud.
2.04.
Yeah, keep going.
921H023.
Okay, that's what it gives you.
Yeah.
Okay, and that's pretty accurate as far as what we have to do for our calculations. But you need to know that, if you're trying to land, land on the moon or another planet, that's why they need supercomputers in order to calculate that. Because if you're going, 100 million miles to Saturn or however far it is, it's really far. It's not that far. I think it's 12 million. But they have to have it so precise, and that's why you need supercomputers to even do space travel. Because our calculators don't go that far, and then we miss the planet by a ton, really far. So we got the number. Gene, what's your question?
So I just want to get with you. A base is basically, it tells you how many ones you add before you add a decimal place. Right. So if it's like base 10, you add 10 ones, then you add a decimal place, and you add 10 more ones, you add a decimal place.
You get it? No. 10 more ones would continue to count up. Our tens digit now goes.
So now you add 10 more tens.
So you add 10 more tens, and then we get 20. You add 10 more tens, you get 30. And as you do that, it still has the decimal place value of being 10 times as large. So then the tens digit goes 10 more, and then you add another digit there.
Okay.
Yeah. Otherwise, numbers would be wild. You count to 20, you'd already be at like 100. All right. So that's just like the basic general of that. Let's look at. Let me see. All right. Let's look at rewriting a few, which they're up here. Let's go ahead and start. This is really our classwork, so I'm going to let us work on it together here. I want you to rewrite number 1. Rewrite number 1 in logarithmic form, because otherwise, here we have 10 to the 5th is equal to 100,000. I like to think first, what's my base? What's my base? 10. So I know that's 10. It's going to be log of 10. Or sorry, log base 10. Of what? Of 100,000, which is essentially saying 10 raised to what power gives us 100,000? And the answer for that? 5. So, yeah. Yes, I can't see, huh? Aaron, can you pull that from there? Or Ellie, can you pull it? So Aaron can pull it. Leave like a little bit of room. Better? Okay. So, you know what I can do? It's also better on this side if I put the... That's glare, right? Okay. So, the pencil or the pen was running out there, so it's a little bit hard to see. But we had... This is equivalent. So this is equivalent to this statement, right? It's equivalent to that statement. This is just practice on you getting the notation down really well. Okay. So looking at those, maybe we need to do like the number 8 as well. Let's do the number 8 so we go the other direction. Is this going to be pretty straightforward as far as just, this was a very easy entry day. Just getting us used to what these things do. Okay. So if I'm looking at this, what if I'm starting with number 8? I decide to start at the end. Log base 10 of 10 is equal to 1. Go ahead and change that into our form here, just numerical form of exponents. No logs, just exponents. I think actually the back. Hold on to this because I think the back of the sheet we're gonna try to work some out tomorrow. More of that exploration. Okay. And you might look at this and you say, well, this doesn't look so bad actually. It's not so bad. I always try to first relate, but I'm trying to give you ways to relate this before they get confusing. Okay. This is my base, right? So I know that my exponent has the base as well. So that's where that goes. And then you're asking, what were we trying to find again? We were trying to find the beginning, 10 raised to what power gave us 71. So that's what we were searching for. We were searching for 10 raised to what power gives you 71 in our intro, or 112. So in this case, it's going to be 10 raised to what power gives you what? Raised to the first power gives you 10. Okay. It's just going the other direction. I first identify the base, and then remember the name of the game is you don't know the exponent. You're trying to find what the exponent is, so you take the log of that value. So, for instance, yeah, this is in essence our a value. 10 raised to what power gives us 10? Well, you didn't see that. Maybe you see it's 1, but otherwise you could take the log of 10, and you get the answer 1. Okay. Gene?
So just to clarify, so for the last. Okay, yeah, no.
You got it now?
Yeah.
Yeah, it's just the reason we only put 8 of these up for you today because it's really just getting used to the spatial aspect of it. So let me see if there's one more thing I want to do with this. And we're almost out of time. Yeah, 6 more minutes. Okay. Okay, so let's go ahead and go one step further. One step further for this, because the inverse operation of an exponent is a logarithm. So if we need to find the inverse of this, because we're going to start to graph these as well. The same ideas around inverse are relevant. It's when y is equal to x, we're reflecting across that axis. Looking at the first quadrant where it's increasing. If I wanted to find the inverse of this, it's already in the notation I need. It's not in function notation. What is that step that we do next to see what is that inverse going to be? We're going to do what? Switch it. Okay? Go ahead and switch it. And we'll see in this pretty straightforward example, we get to this point. Okay. Now, how am I going to interpret and figure this out from here? Because what do I need to solve for whenever I do the inverse? I'm solving for the new y variable. So in essence, I want to find what this is, right? So if we go with that, then we end up with y is equal to, and I want you to go ahead and maybe check through, neighbor if you're confused on it. But what is the log expression going to be in order to find that exponent? And that will arrive us at finding the inverse of a basic exponent problem, exponential problem. So first identify the base. I like to put that where it needs to go. And what's next? How did it relate to this up here? Right? How did that relate? I like to relate and think of the exponent as our a value, if that helps you a little bit to kind of follow through what's been associated with that a value, our exponent. All right, give you another moment. Maybe check with your neighbor. If you're confused on where we're going, remember we were finding the inverse of this starting function. Switch them. Once you switch to find the inverse, you then solve for your new y. So how do we know what that new y is going to be? What is the? You're not going to actually find the tangible actual value, but we're going to write the expression here and be done with it. Gene, what do you think? So the function notation for an inverse.
So, yeah. Equal to log.
Okay. So in essence, you had, well, I don't know what to do with capital. Log of x. Because in order to find what our y value is, we take the log base 10, which is implicit, because that's the standard base, log base 10 of our value x. Just like up here, we had 10 raised to what power gives us 112. We take the log base 10 of 112 to find that exponent. So this right here, this is our inverse of this exponential function. That's the key. That's the key for today, is getting to that one point. So tomorrow we're going to play a little bit more with the exponent rules and how they work with logs exactly the same way. But did you guys feel pretty comfortable with the logs, or sorry, the exponents? Like if I say this, you know, times x to the third power. We multiply them, so what do we do with our exponents? Add them. So this would just be x to the 2x plus 3, right?
So would that mean to be 2x plus 3 equal to log x? Wait, no, log x. No.
No?
Yeah.
Yes? Right, so it would be that actually from this we'd have 2
X
plus 3.
log x.
Well, this would have to be a function, so yeah.
The log x.
Yeah. So if we had what this was equal to, then we could find what we raise x to in order to get that value. What we raise any value to. Well, we'd have to solve for x. There'd be different variables. There would be x next. Tomorrow we're going to hit that. All right, you have these 8 questions. They already, I have a picture of this, and it is on Edmodo, so don't worry about that. And that's it.